Well, hello again, everyone. Welcome to our discussion of section 11.4, where we will talk about conic sections again, but this time the center of the conic sections will be at some other point than the origin of the xy plane. Okay, let's get started. So suppose the center of the conic section is at some point h comma k, and this is usually in books. The authors use h to refer to the x component of the new center and k to refer to the y component of the new center. And I've tried to be consistent with the notations used by the author of your textbook. So that's where that is coming from. So this is the coordinates of the center away from the origin. So let's tie all of this to what we already know. For ellipse, for example, or we can begin with parabola because we covered that in section 11.1 before ellipse. So for parabola, which we first talked about in section 11.1, so we started by talking about parabola when the center was at the origin, right? Something like that. We said that for a hyperbola or parabola that looks like this, the equation of the parabola is x squared equals 4py, right? Now, if the center is at some other point than the origin, suppose if we have this kind of parabola, something like that, and the center is here, someplace else than away from the origin, then the formula will adjust. This formula will adjust itself by taking into account this coordinates of the center. So we will say that x minus h squared equals 4p times y minus k. Notice that the k is associated with the y-axis, and h is associated along with the x-axis. So that's how you see the transition is taking account of the coordinates of the center of this center. So here, this vertex or the center, in this case the vertex, it would be x or h comma k. Okay. So also we could have a horizontal parabola, something like this. And if we had the parabola going through the origin like this, then the formula for this was y squared equals 4px. All right? Now, what happens when the vertex is no longer at the origin? This formula should adjust, right? So if we have a parabola like that, where the vertex is here, some point, let's call it h comma k, that vertex, then the formula will adjust by becoming y minus k squared. Again, k is associated with the y, right? And h is associated with the x, equals 4p times x minus h. And let me box these new formulas like that. Okay, so that's how we adjust the formula. Let's do the same thing for the ellipse, which is what we covered in section 11.2. Okay. Again, let's recall what we talked about in this section, which was any ellipse, horizontal or vertical, that had its center at the origin. So if we had an ellipse that looked like that, the formula for that, the major axis is along the x-axis, right? So the formula for that would be x squared over a squared plus y squared over b squared being the length this from the origin to that vertex along the minor axis. So that is equal to 1. And then when we transition to what happens when the center is no longer at the origin. So suppose our ellipse was somewhere up here, and we had a center, it had a center like that, h comma k, then this formula adjusts accordingly. So we'd have, this is still a horizontal ellipse, right? So x minus h squared divided by a squared, because the major axis is still along the x-axis, right? Plus y minus k squared divided by b squared, and then equals 1. So that's that. And then, of course, an ellipse could be vertical. So let's also discuss that. So we could have a vertical ellipse like that. So in this case, major axis is along the y-axis. So we'll have y squared over a squared plus x squared over, or let me make this. So this would be x squared over b squared. So x squared is over the quantity that is associated with the minor axis, and then y squared over a squared, of course, because the major axis is along the y-axis. So equals 1. I'm trying to be consistent with what your book shows, but you could put this on this side and say plus x squared over b squared, as long as you know that in this case the quantity associated with the major axis should be the denominator of the y squared term. Okay, so then what if how does this change, how does this formula change if we have the vertical ellipse with its center away from the origin? Let's look at that. So suppose if we have an ellipse over here with its center somewhere here, and that center has coordinates h comma k, then the formula should adjust also. So we'll have, I'll try to fit it here, the whole formula. So we have x minus h squared over b squared plus y minus k squared over a squared equals 1. And that's our new formula there. Okay, so let's do the same thing for the hyperbola, which we talked about in section 11.3. So the hyperbola, so here's the hyperbola with its center at the origin. Suppose if we have a hyperbola that does like this and like that. Right, so right now the center is at the origin. And what did we say about the formulas? It had two formulas, one for the hyperbola and the other one for the asymptotes, right? The asymptotes there. So this hyperbola is vertical one, and so the vertices have to be along the y-axis. So we have y squared over a squared minus x squared over b squared equals 1. And of course, the equations of the asymptotes are y equals plus or minus a over bx. So how does this change when the center is no longer at the origin or away from the origin for a vertical hyperbola such as this one here, and maybe like that? So the center is here. Center for this hyperbola would be somewhere here. Let's call it h comma k for now. So this formula should adjust, right, for this shift for the center being away from the origin. So we'll say y minus k squared divided by a squared minus x minus h squared divided by the b squared equals 1. And of course the asymptote, the equation for the asymptote should change as well. How would that change? Well, it's in the same way. So we'll have, instead of y, we will have y minus k equals plus or minus a over b times x minus h. And I apologize for cramming all this, the graph and the formula there. I want to keep this to one page for after I post this on Canvas, all this lecture notes. You have everything on one page. That's why. So you can look at all these formulas and all these graphs on one page. And I think there's a pattern there that it would be good if you pick that up visually, how everything is tied. So that's why I want to try to avoid putting this on different pages. Okay. So let's do the same thing for the horizontal hyperbola. Right? So if we have a horizontal hyperbola here, let's say like that and like that. The center here is at the origin, right? So we said that the formula for this, and notice that the vertices are along the x-axis. So we will have x squared, the formula for this is x squared over a squared minus y squared over b squared equals 1. The equations of the asymptotes would be y equals plus or minus b over a times x. And by the way, let me box this one as well for the vertical hyperbola, and we're doing the same thing for the horizontal one. So like that, like this. And suppose we have a hyperbola that does something like this, like that. I should draw my curves more smoothly, like that, like that. The left one is better. So this curve should be smooth, not sharp. So that's better. Okay, so we know that the center is somewhere here. Let's call this h comma k. So now these formulas should adjust. This time we're going to have x minus h squared over a squared minus y minus k squared over b squared, and of course that is equal to 1, right? equal to 1. I'm barely able to fit it there, like that. And then let me write the equation of the asymptotes right underneath it. So check this out. Now it's going to adjust, right? So y minus k equals plus or minus b over a times x minus h. Like that. Okay. So when I post these notes on Canvas, they will look a lot better because you're going to have everything on one page, which should be good. Okay, so let's use these formulas in examples. Okay, so we have in this example, we want to find so this ellipse is given to us. As a matter of fact, I should have put it right after that. So this ellipse is given to us as x minus 3 squared over 16 plus y plus 3 squared equals 1. That's the ellipse we're talking about. The equation is being given to us. And so given this, we want to find the center of this, the foci, or the focal points of this, and the vertices of this ellipse, and determine the lengths of the major and minor axes. Then, of course, they're asking us to sketch the graph. Like that. Okay, so the easiest thing is compare this with the general equation of an ellipse that we introduced, right? So here, compare that with x minus h squared over a squared plus y minus k squared over b squared equals 1. Compare that with that, and you'll see that the center is at, so what is h? Compare this with this. What is h then? It should be 3, right? Minus 3, so h must have been 3. Then for the k value, what is k? Notice this is in the general equation, it's minus, but now it's positive. So k must have been in here. K must have been what value? Minus 3, right? Because then the minus 3 will give us the positive 3 that we see in the given equation. Okay? I hope you're catching this as you watch the video. Okay. So that's very important because when we locate the focal points and the vertices, it should be off of this, not the origin. Okay? All right, so looking at this again, the information given to us, we know that because a squared is equal to 16, right? Just comparison. A squared equals 16. Therefore, a must be equal to plus or minus 4 away from the center, away from 3 comma negative 3. In which direction? Horizontal or vertical? We know it should be this or plus or minus 4 away from this. But in which direction? Should it be horizontal or vertical? Well, the quantity associated with the major axis, which is A, is under the x squared term for this equation. So that means our ellipse is horizontal. And we're looking at the major axis, which should be along the horizontal direction. So this would be, A would be plus or minus 4 away from this in the horizontal direction. So horizontally. Okay, that means the major axis is equal to, let's first find the vertices. It'll be plus or minus A would be plus or minus 4 away from this point horizontally. So 3 plus 4, 3 minus 4. So we'll have 3 minus 4, comma, minus 3, and 3 plus 4, comma, negative 3. That's what it means when we say horizontally. So this shift is not along the vertical axis. So minus 3 stays. The vertical axis or the vertical or the y component stays what it was. We're shifting the vertices away from this along the horizontal. So it's changing the 3, not the negative 3. Okay, so A should be, let me move this up. So it should be at negative 1, comma, negative 3, and 7, comma, negative 3. And let me box this. So that's the center. These are the things that they've asked us. That's the major axis. But they asked us for the length. So the major axis length, therefore, I wanted to put it up there, but it's better if I write it here underneath this, I think. So the length of the major axis is from this edge horizontally, from negative 1 to 7. So that is major axis length, I should say. Those are the end points, right? So from here to here is 8 equals 8 units. Everything that I'm boxing are the information that they're asking for here. Center the vertices along the major axis and the length of the major axis, which is 8. So let's do the same thing for the minor axis. So because from this equation, b squared equals 1, right? We know that b squared equals 1. Therefore, b will be equal to plus or minus 1 away from this. In which direction? Horizontally or vertically? Well, the major axis is horizontal. So the minor axis for the ellipse has to be vertical. So this plus or minus shift is from this center vertically. Right? Minor and major axis should be along different axes. So we know that the major axis was horizontal. So the minor axis, which is associated with this quantity, B, should be along the vertical axis. So plus or minus 1 away from this point. So let's find that out. So B would be equal to 3 comma negative 3 plus 1 and plus 1 and negative 3 minus 1, right? Plus or minus 1. Okay, so we have B in this case. We have 3 comma negative 2 and 3 comma negative 4, right? And these are the vertices of the ellipse along the minor axis, and they also asked us for the length of the minor axis. So let me write that down here. Minor axis length, that would be difference in the vertical direction, right? From -2 to -4, that's just 2 units. So that is equal to 2. Like that. Okay, let's find the focal point, right? That's what they also asked us. So because c squared is equal to a squared minus b squared, then we have a squared, we already know is 16, right? From here. A squared is 16, b squared is 1. So let's plug in. That will be 16 minus 1 equals to 15. So we know that c squared equals 15, right? That's what we just calculated. So therefore, c is equal to plus or minus square root of 15, or c is equal to, well, let me write it here because I'm not going to have enough room there. So therefore, after that, so let me make that an arrow in this direction. So c is equal to, let me calculate this. Let's calculate that. What is that? We want to know what is square root of 15, because we're going to have to graph it, so it'll be better if we know. Okay, so that's what it is. So I'm going to round this to 3.9 because drawing graphs manually, we don't need, or I can't even draw 3.87. So 3.9 is a better number to use when we graph manually. So I'm going to use that. So c is equal to plus or minus 3.9. Okay, so is this going to be along the horizontal axis or along horizontal or vertical? Well, this shift will have to be along the horizontal because the focal points of an ellipse are always along the same axis as the minor axis, and this as the major axis. I apologize. So the focal points are always along the same axis as the major axis, and in this case, our major axis is horizontal. So I'm going to have to. So this will be this away from 3 comma negative 3 horizontally. Okay, so that would be, let's find that. So this would be 3, let's see, 3 minus, yes, so 3 minus, or let's see, minus 1. So we have minus that and plus that. That will be within. I'm trying to compare. So when I'm minus 3.9. Yes, that would work. So we'll have 3 minus, right? The shift is horizontal. So 3 minus 3.9. The vertical component stays as it was, and 3 plus 3.9 comma negative 3. Notice how the shift is affecting in the x components because that's the horizontal direction, and it's not changing anything with respect to the y components, right? So the shift is horizontal, the shift for the focal points is with respect to the major axis, right? Not along the vertical axis. Okay, so let's simplify this. We have, this will be minus 0.9. Right, so let's see where this will land. So we have minus 3.9, so this would be at minus 2.9, right? That's no minus 3 minus 0.9, and so minus 0.9 here. Yes, that should be okay. Minus 3, and here we have 6.9 comma negative 3. Okay, so let's plot these points. We have everything we need. Let's see if this is, I just want to double check my numbers here. Minus 0.9 and 6.9. So this will be, I think that should be okay. Major axis from the center. So that should be okay. Minus, let's see, so these are away from the center, plus or minus 3.9 from that, and let's see, so this 9, and it should be okay. Yes, so let's draw this. I will try to fit this at the bottom of this page. Now, most of this ellipse is below the x-axis, so I will give most of this space to the negative side, like that, and the vertical axis, like this. And so we have, let's see, so the center is at 3 comma negative 3. Let me, so 1, 2, 3, 1, 2, 3, 1, 2, 3. So 3 comma negative 3 would be here. Let's increment this 1, 2, 3. That. So the center at 3 comma negative 3, that would be here. So the major axis has to go through that center. Like that. And the minor axis should be vertical, going through the center, like that. So looking at these values, the end or the vertices along the major axis are at these locations. I'm going to plot these 2 points, -1, -3. That would be that point right there. 7 comma -3, I need to add some increments here. So 4, 5, 6, and 7. 7 comma -3 would be right here. Okay, and the minor axes are right there. You can see them here. I'm going to plot these two coordinate points. So 3 comma negative 2. 3 comma negative 2 would be here. And 3 comma negative 4 would be on that side. So negative 3 is right there. Negative 4 would be here. Here. So 3 comma negative 4 would be that point here. So this is a very narrow or squished ellipse. It's squished in the horizontal direction. So let me draw this ellipse. So it should look like something like this. Like that. But I haven't found the location of the focal points yet. So that'll be -9 or minus 0.9. Minus 0.9 comma negative 3. So minus 0.9 would be here. It would be very close to the vertex here. So right there we have F1, and F2 would be also very near here. F2 would be here inside the ellipse. Okay, so that is if you want, we can label these vertices also. So we have this at 7 comma negative 3. This end is at -1 comma negative 3. And let's see, so we have, and this point was 3 comma negative 2. This point was 3 negative 4, and the focal point, so the center is at 3 comma negative 3. It's making this drawing a little bit crowded, but it's okay. I want to put as much information as I can on the drawing. So what else? We have all that done. And so, the focal points as well. And so that would be, let's see, so that would be this one. I don't know what, maybe I should put it here. So that would be, say, F1 at -0.9 comma negative 3, and F2 at 6.9 comma negative 3. Okay, away from the center there. Okay, so let's look at another example. So in this case, we want to find the same type of information, or a little more different because parabola is different. The parabola has the directrix, but the ellipse doesn't have that. So find the vertex, focus, and directrix of the parabola. Of this parabola, here's what the information we are given. Y plus 5 squared equals -6 plus 12. And of course, they're asking us to sketch the graph. And sketch the graph. Okay. So what I would do is first, let's compare that. So compare with this general equation, y minus k squared equals 4p times x minus h, right? Right now, it seems we don't know anything about 4p, so let's factor the right-hand side. The left-hand side is okay. Right away, we know that k has to be -5, but the right-hand side isn't the way, it doesn't look the way we want it, so let's factor the right-hand side. So factoring the right-hand side, we have y plus 5 squared minus 6. Let's factor -6. So what do we have left? X minus 2, right? X minus 2 we have left. Okay, so now compare this with that. We can now know that the center is at So comparing with this with that, what is the h? What is the value of h? Compare this with that. It is 2, right? Positive 2. Comma, how about k? What is the value of k? It should be -5, right? Like that. So that's the center. And then to graph, they want us to find the, so that's the, or center, or I should say vertex in this case. So center, I was thinking about the ellipse still, sorry about that. So let's call this vertex. This is what they have asked us. We have that. And the focus and the directrix. So that, the focus and the directrix have to do with the value of P. So we need to, in order to answer the question for focus and directrix, we need to know what P is. Compare that with this. The P we have to calculate, right? So 4P in this case equals -6, right, after we factor. So P is equal to -6/4, or after simplifying, P is equal to -3/2. Okay, so before we give the actual equation for the directrix, and the coordinates of the focus, we have to know in our mind, we have to have an idea in which way this parabola opens. So notice that it's a y squared, not x squared. That means y squared, let me bring this back so you can see it. When you have y squared equals that, which has this equation, the parabola opens horizontally. So if this was negative, it would open to the left. If it's positive, it opens to the right. But it opens horizontally if you have y squared. This is certainly y squared. And certainly we have a negative in front here. So it's horizontal parabola, and it opens to the left, not to the right. Because of this negative, it opens to the left. So because it opens to the left, that means the directrix should be on the right-hand side, right after the vertex of the parabola. And the focus should be on the left, or on the left of the vertex, right? So let me write that down just to make sure that you have this. Because the parabola opens to the left horizontally, the focus point should be to the left of the vertex, that, and the directrix should be to the right of the vertex. Right? Remember, in parabola, the vertex and the focal point and the directrix are on opposite sides of the vertex. Okay, so we now know that. What else do we need to know? Okay, so let's find out where the vertex and or the focus and the directrix are. And then we can sketch the parabola. So the focus, this is a horizontal parabola, right? So the focus is minus, based on what I just wrote, the focus will be, point should be to the left of this vertex. To the left of this, that means 2 minus or 2 plus that. So that'll take care, the minus will take care of that. So we have 2 to the left of that will be minus 3/2, which is equal to, if we take the common denominator, we end up with 1/2. So, so the focus is at point 1/2 comma -5. Okay, that's that. Now the directrix. The directrix is on the opposite side of the vertex, right? So we have to add, to be on the right of this point, we need to add 3/2 to it. So think of this as a distance measure that has to be added to this. So don't think of it as a negative. Here we subtracted because the focus is on the left of this parabola that opens to the left. But the directrix should be on the opposite side, should be on the right side of this. To be on the right side of this, we have to add 3/2 to that, right? So let's do that. So we have 2 plus 3/2. This is 1.5, this is 2, so that's 3.5, or 7/2. Okay, so the equation of the directrix is equal to x equals to 7/2. Okay, so we have the focus, we have the directrix. Now we can draw this parabola. Let me. Once again, the most of this graph is below the x-axis, so I'm going to draw my axis to give me that space that I need at the bottom of this page. So we have that. And this is y. So the vertex is at 2 comma -5. So 1, 2, 1, 2, 3, 4, 5. So 2 comma -5 is right there. That's the vertex. And so it's opening. The the y or the x-intercepts, let's see, so for the y-intercepts, we can find the y-intercepts, right? So where does this parabola intersect the x and y axis? We can find that using the x and y intercepts. So if x is equal to 0, we're going to find the y-intercepts. So y plus 5 squared is equal to 0. So that means y equals negative 5. Let's see. So maybe I can, so if we have x equals 0, so y plus 5 squared, and that'll give us, and then take the square root of both sides, so y equals negative 5, and does that make sense? So let's see. Well, let's first plot the focal point. And so we know that the focal point is along the same line, horizontally, like that. So that'll be 1/2 comma negative 5. 1/2, if this is 2, then 1/2 would be roughly here. So that's the focal point. So this is, that one is 1/2 comma negative 5. And the directrix would be right after the vertex here. So we have, let's see, so we have, so if this is, which is 7/2, right? 7/2 is 3.5. And if this is 2, 3.5, 3, and if this is 4, this is 3. 3.5 is roughly here. So that's the directrix. We're going through midway between 3 and 4. So I will draw this with red ink, like that. And let me say that that is x equals 7/2, or the directrix. Okay, so we can get an idea of where along the x and y axis this parabola will intersect those axes. So if we substitute for x with 0, we get y plus 5 squared. I can do that here. So let me do that here. So the x-intercept or the y-intercept I don't think I'll be able to fit it here. If not, I'll just roughly draw it. But the y-intercept would be y plus 5 squared. Let me move this up a little bit. Y plus 5 squared equals minus 6 times 0 plus 12. So we have y plus 5 squared equals 12. And then take the square root of both sides. What do you get? You get y plus 5 equals plus or minus square root of 12. And if I calculate, it would be 3 point something, right? So square root of 12, it's let's say 3.5, right? 3.5 plus or minus 3.5. So this would be plus or minus 3.5. So the y-intercepts would be along, so that would be along this right here. So it would be 0 comma 8.5 and 0 comma minus 8.5, right? Let's see, let me make sure that this, no. So this is minus 5 plus 3.5, that would be minus, I'll do that here. So so one of them would be minus, let me add that here. If we solve this equation for y, we get 0 that, comma, minus 8.5. And then the other one would be minus 5 plus 3.5. It'll be minus 1.5. Like that. Okay. So where are these? Let's locate these on here. If this is minus 5, this minus 6, minus 7, minus 8, minus 9. Right? Because that line is going through minus 5. So minus 8.5 would be somewhere here. That's the y-intercept. And the other one is at minus 1.5. If that's minus 1 and minus 2, minus 1.5 is right there. So these are the y-intercepts of this parabola. And the x-intercept would be, we can calculate that. Let me, because I have only this space left here. So the x-intercept, so we have 0 plus 5 squared equals minus x plus 12, right? That's the original equation. Oops, let me move this into the view like that. So all I'm doing is finding the x-intercept somewhere there for this parabola in order to make my graph as exact as possible. So what I did was substitute in the original equation for y with 0 to find the x-intercept, right? So the left-hand side now is 25 equals minus 6x plus 12. So now we have move the 12 to this side, you get 25 minus 12, which is positive 13 equals minus 6x. So x is equal to minus 13 over that. So the x-intercept, there's just one x-intercept, and that'll be at negative 13 over 6, comma 0. Okay? So negative 13 over 6, that's going to be something like a little bit over negative 2, right? Somewhere between negative 2 and negative 3. We can plot that, so it's still within this view. So if this is negative 1, negative 2, and negative 3, then that point, the x-intercept, it's going to be here. Okay, so we have a rough idea how this parabola is going to go. So let's draw it. So it's going to have to go through this being the vertex. Right? I don't want to lose my vertex here. Yeah, that's the vertex. So I'll try to do as best of a job I can. So it's going to go through that. Then it's going to go through this. Then it's going to come back and do that. Okay, roughly. And that's the directrix which has that equation. So, sorry for cramming again my page here, but that's the y-intercept, the x-intercept calculation. So we have the y-intercept here, the x-intercept here, and the focus point is here, the vertex is here, and all of that. And of course the directrix, which is equal to, has this equation, equal to 7/2. Okay, so let's do another example. So we want to find the center, foci, vertices, and so this time is a hyperbola, and then sketch the graph. Okay, and this is our, let's see, we have, so here is the equation for the hyperbola, and we have y minus y squared divided by 25 minus x plus 3 squared equals 1. Okay. Okay, so compare this. So compare this with this equation, or this general equation, y minus k squared, right, over a squared, minus x minus h squared over b squared equals 1, right? So comparing that with that, we know that a represents the vertices of the hyperbola, and so at that, so a squared is equal to 25, which means a equals plus or minus 5. But even before that, comparing this with this, maybe you should pause the video, if you would please, and write down the center. What is the center of the coordinates of the center of this hyperbola? Okay, I'm assuming you've done that. You've already paused and you know what the center is. And so let's compare it with this, with the one I have. So center should be at, h must have been negative 3, right? Because minus h ended up being plus 3. So h must have been minus 3. So the center is at negative 3, and k must have been at 1, because minus k ended up being minus 1. So we have that center of the hyperbola. That's very important, because now the a squared and b squared will be measured off of this center, not the origin anymore, right? It'll be these two will be offset from this center. Okay, so let's find for a squared. These are the vertices, so we have a squared equals 25, therefore a is equal to plus or minus 5. Away from the center, minus 3 comma 1. Now the question is, in which direction, horizontally or vertically? Now notice that the vertices are under the y squared term. So this is a vertical hyperbola. Because this is a vertical hyperbola, these distances will be measured off the y component of the center. So it's going to be like this. So we have so away from this. Well, let me first add away from this vertically. Again, because the vertices are associated with the quantity associated with vertices is associated with the y squared term. So this is a vertical hyperbola, and so this shift for the vertices should happen in the vertical direction with respect to the coordinates of the center. Okay, So that's the center, and the shift will happen vertically. So A will be -3. Notice -3 stayed the way it is. 1 plus 5, and then 1 minus 5. And -3 comma 1 minus 5. Okay, so let's clean this up. -3 comma 6 and -3 comma -4. So those are the coordinates of the vertices of this hyperbola. And that's the center. So let's find B, because the coordinates of B will tell us where the corner points of the central box are. Remember the central box? That's where once you identify the central box, the asymptotes that we have, the two asymptotes we have, one increasing, one decreasing line, will go through the corner points of the central box. So drawing the central box makes it easier to know where our asymptotes are. That's why it's useful in that way. But you can also draw the lines themselves. You can use the equations of the asymptotes to do the same thing. But I think knowing where B, we already have to know where A is for the vertices. But knowing B, in my opinion, makes it easier to draw the asymptotes, that's all. But it's not the only way to draw the asymptotes. It's another easier way. Okay, so let's find B. In this case, when you compare, B squared is equal to 1, right? So B squared equals 1, which means A is equal to plus or minus 1. And this is away from the center, -3 comma 1, vertically or horizontally? Well, it has to be horizontal, right? Because the vertices are vertical, are along the, are on a line parallel to the y-axis. The vertices are, right? So the B values should be horizontal. So away from this, horizontally. Okay, horizontally. So let's find them. I wish I had my whiteout with me, but this is -3 comma 1 plus 1. Let me try to correct this. So 1 plus 1 and then -3 comma 1 minus 1. Well, I said horizontally, so let me correct this. Before I post this on Canvas, I will white these out. So you shouldn't see this on the version of these notes that I'm posting on Canvas. But for now, let me correct this with a line through them. So it has to be horizontal. So B, and also I need to correct that. This is B so it'll be away from that horizontally. So it'll be -3 plus 1 comma 1 and -3 minus 1 comma 1. Okay, now it's correct. So let's clean this up. So we have -2 comma 1 and -4 comma 1. So that's the location for B. And so again, I will get rid of that before posting my notes on the on canvas. So you won't even see that. Okay, so what else do we need to know? Oh, we need to know the location of the focal points, right? So so my graph will be on the other page. I won't be able to fit that graph with all these calculations here. So for the focal points, the foci, let's call them, or the focal points, we know that c squared is equal to a squared plus b squared for the hyperbola, right? For ellipse, it's different. It's a squared minus b squared for ellipse. Remember that? But here it's a squared plus b squared. So a squared was 25, b squared was 1. I'm looking at this. 25 a squared and b squared equals 1. And plugging in. So we have 26. So if c squared is equal to 26, therefore c is equal to plus or minus square root of 26. And let's take the square root of that. Oops, wrong button there. Square root of 26. So roughly, let's round that to plus or minus 5.1. Okay, so c equals plus or minus 5.1. Now this is away. The focal points are along the same axis as the vertices are. So the vertices, we decided that were vertical. So this is plus or minus 5.1 away from this, the center. Vertically. Okay, so let's find them. So we have, let's see, the center was -3, so this away from the center, and the center is -3, 1. Right? So let's find the location of the focal points. So C are -3, 1 plus 5.1, and -3, 1 minus 5.1. Okay, so what do we end up with? We end up with the location of the focal points at -3, 6.1 and -3, -4.1. So that's the location of the focal points. Okay, so let's graph, the asymptotes. I have to go to the other page. So this is solution continued. I'm going to use the central box to draw my asymptotes, but I still want to calculate the equation of those asymptotes. So we have that, okay? The exact equation, we should have that. Okay, so for the asymptotes, we have y minus k equals plus or minus a over b times x minus h. And so where h comma k, we know in this case, is equal to -3, 1, right? We know that. So let's plug in. We have y minus 1, k is 1 in this case, equals plus or minus a over b. We know that a let's see, a was, so plus or minus 5, that takes care of the plus or minus 5 here. I mean, the plus or minus 5 in the equation takes care of that too. So A over B, A was plus or minus 5, B was plus or minus 5, sorry, plus or minus 1, right? A was plus or minus 5, B was plus or minus 1. So 5 over 1 times x minus h. So that would be plus 3, right? Plus 3. All right, so let's simplify this. So this would be just y minus 1 equals plus or minus 5 times x plus 3. And then, of course, we have we're going to have 2 equations, right? As we should, because we have 2 asymptotes for the hyperbola. So let's let's find one equation on this side and one on that side. That's one. And that's another one. So minus 1, move it to the other side, add it to 15. We get 16. That's one of the that's one asymptote. One asymptote. That's the one that is sloping uphill, right? Increasing. And that one should have a negative slope. And it will have, right? So y minus 1 equals minus 5x minus 15. And then y equals minus 5x. Move this to the other side, you get minus 14. And this is the other asymptote. The other asymptote. Okay. Again, this is just to know the equations for those asymptotes, because when it comes to drawing them, we really didn't need these because we have A and B, which give us the central box, and the asymptotes do go through the center of the hyperbola and through the corners of that central box. Okay. All right. So now we have everything that we need and more to draw the graph of this hyperbola. Let's do that here. This is going to be a vertical hyperbola, so I'm going to draw it here. That'll allow me to make use of that space. Hopefully I can catch everything or show everything on the screen like that. I think that should be plenty of space there. Most of this is to the left of the y-axis, so that's why I want to draw my y-axis here, so to give me enough space on that side. That's way too, but that's what it is. Okay, so I'll be going back and forth between these pages so you can see what I'm doing. So the first thing I'm going to plot is the center. It's going to be at negative 3 comma 1. And I will show that. So negative 3 comma 1 would be 1, negative. That's negative 3. And 1, that would be 1. And I will just increment more here because I'm going to need these numbers. And one more. I think that should be enough. Okay. So the center of this hyperbola at negative 3 comma 1 would be here, negative 3 comma 1, right there. Right there. So the A and B, this is a vertical hyperbola, so the vertices are going to be along this line, this vertical line that goes through the center, like that. And of course, to draw my central box, I'm going to draw a horizontal line, dashed line, right through the center as well. So it makes it easier for me to find B. Okay, so we know the center. Let's plot the vertices, which are vertical. So one of them is going to be at negative 3 comma 6. Let's find that. Negative 3 comma 6, that's right there. And so that is negative 3 comma 6. The other one is going to be at negative 3 comma negative 4. Let's find that. Negative 3, negative 4 is right there. Right there. Like that. And B, let's find that. One corner is going to be at negative 2 comma 1. So negative 2 comma 1 would be right there. Right? Negative 2 comma 1. And then the other one is going to be at negative 4 comma 1. So negative 4 comma 1 would be here. That's negative, that's negative 4. That's negative 4 comma 1. So it'll be right there. Right there. Okay, and maybe I'm sure my increments are off, but there should be an equal distance from this minus B to this plus B. Okay, so let's draw the central box. I will make it dashed. Like that. And then let me also draw another line that goes through this side. I'll try to make my graph as good as I can manually drawing this. Like that. And then also like that. Like that. Okay, so that's the central box. Then let's draw the asymptotes. So it'll be like that. Oops, it didn't draw part of this, so let me try again. Notice the asymptotes are going through the corner points of this central box as well as the center of the hyperbola. So I'll do the same thing on this side. So I want to go through that center right there, like that. We know the equations of these asymptotes, right? One of them is going to be associated with this uphill sloping line. Let me move this up a little bit. So I'm going to put right on top of this line, this asymptote, the one that has a positive slope. Y equals 5x plus 16. So y equals 5x plus 16. And the one that has a negative slope, I'm going to put that on this line. So it'll be y equals minus 5x, minus 5x minus 14. Okay, so we have that drawn up, and then of course we know that this is a vertical. So the vertices are at negative 3 comma 6, and this one, which I haven't labeled yet, but the way it looks, it should be negative 3 comma negative 4. Yes, it is. So this is negative 3 comma negative 4, and this one on this side, I mean, it's getting, this one is already getting crowded, but I want to give you as much information as possible. So that point is at negative 4 comma 1. That's that point. And the center, of course, is at negative 3 comma 1, but it's been covered right there. So negative 3 comma 1, that's the center. Okay, so we can easily draw the hyperbola. One is line comes here and curves back up, goes like that. And the other one is doing the same thing down here, like that and like that. Okay. All right. So let's look at another example. Here we want to find, okay, so this is different now. Here they are giving us the graph, and they want us to look at the graph and write down the equation for this parabola. So it says find an equation for the parabola whose graph is shown. And here's the graph. Like that. And I need to actually extend this x-axis a little more, otherwise I won't be able to draw my directrix. That's better. So the vertex here is at negative 6 comma 0. So we have, let's say that's negative 1, negative 2, negative 3, 4, 5, 6. And here they tell us that this is, they tell us that that's 5, that is 10. So this should be negative 5 and negative 10. So that's the vertex here. And the parabola looks like this. Like this. And like that. negative 6, comma 0. And okay, so that's, they also tell us where the directrix is. The directrix is at y equals negative 12, so that's negative 6, negative 7, 8, 9, 10, 11, and 12. And so let me draw that with this. Oops. And this, the equation of this directrix, of course, is x equals minus 12. Okay, so then according to this set of information that we have, the vertex and the directrix, then first of all, look at the shape of this parabola. It opens towards the y-axis. So let's use that to our advantage. So here's the solution. So because the parabola opens towards the y-axis, then the general equation must have this form. Of the form y minus k squared equals 4p times x minus h. Okay, that's just, we know that looking at the by looking at the graph. Okay, so we already know the center. Let's plug it in, right? We know that from this the h comma k, also we know that h comma k is equal to minus 6 comma 0, right? So let's plug into this general equation with this information about h and k. So we have then y minus 0, k is 0, squared equals 4p 4p times x minus h. H is minus 6, so plus 6. Okay. So like that. Also, we know that just looking at the graph and the distance between the vertex and the directrix, see, the distance from the vertex and the directrix should be the same distance from this vertex and the focal point for this parabola. We know that. So we know that the distance from the P in this case is from here to here. So we know this distance is P. Right, P, and that should be equal to positive 6, right? So that's distance. So P, that distance, is equal to positive 6. So the focal point should be 6 points to the right of this vertex on this side. So the focal point, not the vertex, but the focal point for this parabola would be at the origin. But the importance of this directrix is that we are given that information, is that it tells us what P is. P itself is positive 6. So I guess I wrote here what I should have probably written here. So first let me clean this up. So this will be y squared equals 4p times x plus 6. Also, because the directrix is at x equals negative 12 and the vertex is at negative 6 comma 0, then because of that, that's what I did up here, but I'm just making a note about it, then P would be equal to absolute value of negative 6 equals positive 6. So in this equation, we can then substitute for P with 6, and we have our equation. So then from here to here, we have y squared equals 24 times x plus 6, right? Just plugging in for P with 6, we have 24 there. So that's the equation of that parabola. Okay. Another example, very similar to this. So again, we're finding an equation, but this time when we are given the graph for an ellipse. So let's look at that. So in this example, we want to find an equation is shown. Okay, so let's see what the graph looks like. It's a horizontal ellipse. That's as best as I can draw it. Like that. And we know that we are given the focal points here and here at 2 comma 0. We have F1, let's call it, and F2 is at 8 comma 0, and we are told that that vertex here, we know that this vertex is at 0 comma 0, right? That's at 0 comma 0, this vertex, and the major axis goes from 0 comma 0 to, we are told that point is 10 comma 0, that one. So we know the location of the major axis, we know the and the vertices along that, and we know the location of the focal points. And of course, with all this information, well, first of all, it's a horizontal ellipse. So let's take this one step at a time. So solution of this is that because this is a horizontal ellipse, horizontal ellipse with the center with the center away from the origin, because of that, then this should be the equation of the general equation of any ellipse like this. This is the general equation. X minus h squared over a squared plus y minus k squared over b squared equals 1, right? That's the general equation. Now, the a, we already know where the a is, right? So we have the center is going to be halfway between the two vertices, 0, 0 and 10, 0. So the center of this ellipse is at 5, 0. Right? Just knowing that. So A is the distance along the major axis from this vertex to the center. So this distance is A, and it's equal to 5. Okay. Oh, one piece of information that I didn't draw yet. So we are told that from here, from the top of the ellipse, we are told that that is 4, and this is at -4. That's also given to us. So that is -4. So all of this information is given to us. Okay? And that's important because the minor axis then, the minor axis which goes through the center and from the top to the bottom points here, that has to be 5, 4, and this point has to be 5, -4, right? So B is plus or minus 4 along that axis. Okay, so with all that information given to us, so let me write here, from the graph, the length of the major axis is equal to 10, right? From here to here, it's 10 units. So, thus 2a equals 10, and a, because that distance from here to here is 2a, so a is equal to 5. Okay? And then from the graph again, I'm trying to keep the graph on the screen as I write this down. So the length of the minor axis is equal to, looking at this, it's going to be 8, right? So that's 8. So thus, but the length of the minor axis is 2b. So 2b is equal to 8. Therefore, b is equal to 4. Okay? And the center And once again, I'm running out of room here, but so I'm going to write down from the graph, the center is at 5, 0. So from the graph, center is at 5, 0. Okay, so now let's move this up. So you know where I got those pieces of information from the graph. So taking all this into account, and the fact that the general equation of the ellipse for this ellipse is like that, for a horizontal ellipse that has its center off or away from the origin is like that. Let's plug in. So we have x minus h is 5, minus 5, right? H is 5 squared over a squared. A is 5, so a squared is 25 plus y minus k. K is 0 squared over b squared. B is 4, so it's b squared is 16 equals 1. Okay, so the 0 goes away, right? So we can simplify this equation. We get x minus 5 squared over 25 plus y squared over 16 equals 1. And this is the equation of that ellipse. Okay. So let's do the same thing, but this time for a hyperbola. For the hyperbola whose graph is shown. Okay. So we are shown in this graph that suppose if I take this at 1 and this point at 2, so this is 1, this is 2, then and also from here so this is 1 and this is negative 1. This is maybe this is a little bit too so this is, let me lower this increment a little bit like that. Okay, so let me draw this. We are shown a central box like that, and one side is this x-axis like that, and then also like that. So this line is going through y equals 2, but but on my graph I should do a better job of showing it. So this point is 0, 2, that point. As a matter of fact, let me say, so I don't want to make the drawing too crowded, but that point is 0, 2, that point. Okay, and that also, which is here, then we are shown the asymptotes going like this. And another one going like this. So this is the center of the hyperbola right there at 0, 1. Like that. And we are shown that this is a, because notice in this one, A and B are equal, right? They're equal to 1. From here to here, from here to here, from here to here, that's equally distant. So, and it's 1 unit. So A and B are equal, but we are shown that this is a vertical hyperbola. So I gotta draw it like this, like that. And also like that. Okay, so this is, let me just give more. So this is 1 unit, so this is 1, 0, that corner. And this is -1, 0. And so that point is 1 or 0, 1. That's center. And that corner point here is -1, 2. That point is -1, 2. And that point is 1, 2. Okay. So given this hyperbola, we are asked to find the equation for it. Well, first of all, so because this is a vertical hyperbola, with a center away from the origin, then in this case, the vertex or the vertices, this vertex and this vertex are along the y-axis, right? So we have y minus k. So let me write that down. Y y minus k squared over a squared minus x minus h squared over b squared equals 1. Okay? So because of that, so the vertices are along the y-axis. They could be off the y-axis somewhere here. Still, the general equation for that would look like this. But the center here is not at the origin. It's at 0, 1. We know that. Okay, so because of that, so from the graph, this is actually, the graph is so detailed, so it gives us a lot of good information. So from the graph, A is equal to 1, therefore A squared is equal to 1. Once again, from the graph, B equals to 1, right? So A is from here, from the center of the hyperbola to each vertex. And we know that's 1. From here to here is 1, from here to here is 1. And then B is from the center to this side of the central box. So that's also 1. So B is 1 here, from the center to this side of the central box is 1 unit. from this center to this side of the central box is also 1 unit. So B is, if B is equal to 1, then B squared is also equal to 1. Okay, so, and we know that the center, so from the graph, let me lower this a little bit. So from the graph, the center is at 0, 1, right? From the graph. The center is at 0, 1, like that. Okay, we're just going to plug in then. So we have y minus 1, right? K is 1 squared over a squared is 1 squared minus x minus h, which is 0 squared over b squared, which is 1 squared, equals 1. So let's simplify this. We get y minus 1 squared minus x squared equals 1. So that's the equation of that hyperbola. Okay, change of a little bit. These next examples are a little bit different than what we've been doing. So, but nonetheless, it's a topic within this section, so we're going to cover it. And so this is the central equation of a shifted conic. Okay. This is the central equation of a shifted conic. And this applies to any of these conic sections that we've been dealing about. So ax squared plus cy squared plus dx plus ey plus f equals 0. That's the central equation of the shifted conic, where let's define those terms. Where a and c, these are the coefficients of the squared terms, right? A and c are not both 0. So they can both be 0. One can be 0, the other one not. Okay, there has to be something other than 0. Are not both 0. Like that. When these are not both 0 is a so it can be is a conic or a degenerate conic. And we'll talk about the degenerate case. The conic ones are the ones we've been dealing with, and the degenerate case we will look at. So I should have maybe written these in red ink, but because they are the main things here in degenerate conic. And so in in the non-degenerate case, that's non-degenerate. So let me say AKA non-degenerate. And I'm trying to use the same terminology that your book uses. So when you read this and you read the textbook, they match. So in the non-degenerate case, these are the cases we've been looking at so far. So in the non-degenerate cases, the graph is 1, so a parabola if A or C is 0. Okay. 2, an ellipse if A and C, A and C have the same sign. A circle if A and C have the same algebraic sign and A equals C. Okay. And we have a hyperbola if A and C have opposite signs. Okay, so this is for a parabola, this is for an ellipse, this is for a circle, and this is for a hyperbola. So depending on, given this conic central equation of a shifted conic, depending on what these A and C values are, we can have a parabola, we can have an ellipse, we can have a circle, or we can have a hyperbola. Okay? So note, let me add that note. I mentioned that I will be talking about the degenerate case. So a note about the degenerate conic. Okay, a note about that. We talked about completing of the square method in Math 126, which is the pre-calculus one, when we were discovering the equation of a circle. Remember that? If you've taken Math 126 recently, maybe last semester, you should remember that we used the method of completing of the square for finding the equation of a circle in that course. So here, in a bit, we're going to use that method again. So if you happen to have forgotten about the method of completing of the square, I'd recommend that you brush up on it before looking at the examples that we are about to go through in a few minutes. I will briefly mention it, but since that was covered in Math 126, I won't give too much details about it. Okay, so a note about the degenerate conic. Okay, so this is of particular importance here with respect to some examples. Okay, so let's see some examples on that. So for this equation that we are being given, for the equation 2x squared plus y squared, right? That's a and c, right? They're both non-zero. Equals 2y plus 1. For this equation, we're asked to complete the square. That will be for the x and y terms. For x, we don't have to do it, right? Because it's the only x term and it's already squared. So we don't have to complete the square for x, but certainly for y terms, we have to do it. Complete the square. Okay, so we want to complete this square to determine whether the equation represents this. And let's see what else they ask us to do here. Or a degenerate. So, because in this slide, we said that a central equation of a shifted conic, defined as that, can be a parabola depending on if it's a parabola, if A or C is 0, one of them should be out, right? We know that from the equation of a parabola. If you look at the equation of the parabola, whether when the vertex was at the origin or whether it was away from the origin, there is only one square term, right? The other one is gone. So if you look back at that, so if A or C is 0, then for the non-degenerate case, of course, this is for the non-degenerate cases, then we have a parabola. If the A and C in this equation have the same algebraic sign, then that would be an ellipse. If a circle, if A and C have the same algebraic sign and the two are equal in value, and hyperbola if A and C have opposite signs. Okay, so we need to discover that. We need to complete the square for this equation and determine what do we have. Do we have, which one of these conic sections we have with this? Or it could be a degenerate case, okay, and we'll find that out too. Okay, so to complete the square for this equation, let's move everything, all the variable terms to one side. Right, we can leave the 1 on the other side. It's okay. But anything with the variable in it, we should move to the left. Let's do that. So we have 2x squared plus y squared minus 2y equals 1. Then x squared is okay. It's the only term and it's squared. We don't have to complete the square. But for the y term, we need to do that. So we have 2x squared plus, we say, y squared minus 2y. I'm going to add 1 here, plus 1. This is to complete the square. Plus 1. I added 1 to these two terms, so I have a perfect square here. But because of that, I have to subtract 1 here in order to balance that equation. So all I did here was basically add 1 and subtract 1. So what's the use of that? The use of that is that now I can write these two terms as part of a complete square. Okay? And equal to 1. And so let's do that. So we can complete this. We can write this as a complete square. So 2x squared plus y minus 1 squared. Now if you expand this, you're going to get that. And then let's move this -1 to the other side. We get 2. 1 plus 1 is 2. Or as you like to say it, add 1 to both sides and you get that. Okay, now let's divide all sides by 2. So dividing we have 2x squared over 2 plus y minus 1 squared over 2 equals 2 over 2, right? So the 2 and the 2 cancel here. We have x squared plus y minus 1 squared over 2 equals 1, right? Okay. What kind of an equation, what conic section is this? Do you remember? This is plus, not negative, so not minus. So definitely this is not hyperbola. So definitely this has to be an ellipse. The other thing I want to ask you here, is this a vertical ellipse or is this a horizontal ellipse? Which one do you think it is? Well, if you look at the denominator here is 1, right? So 2 must be the quantity associated with the major axis in an ellipse. So if the major axis, if the quantity associated with major axis is the denominator of the y squared term, this has to be a vertical ellipse. So it is a vertical ellipse. Okay? So this is our equation, and this is the interpretation we have from it. Okay? Let's do another example. All of this is working with this equation, central equation of a shifted conic. So these are examples of dealing with that. So once again, what we want to do is for this equation, 3x squared plus 4y squared minus 6x minus 24y plus 39 equals 0. For this equation, we want to okay, so we want to do that. Okay, so for completing of the square, we want to keep all the variable terms on one side and move the constant, the only constant or any constant, to the other side. So that's the first thing we will do. And I'm going to keep, not only I'm going to move this to the right, this 39 to the right-hand side, I'm going to move this minus 6x next to x squared term. So the terms that have x in them are together, and the terms that have y terms are together. Let's do that. Like that. Okay? Okay, so now we have to complete the square in each case. But if you recall, when we talked about completing of the square method in Math 126, we said that you cannot complete the square unless the coefficient of the squared term is 1. In this case, it's not, right? So what do we have to do? In order to apply the completing of the square method, we need to factor out the x terms so that the coefficient of the x term stays 1. Okay, so let's do that. So I'm going to factor out the 3 from the x terms. So we're going to have x squared minus 2x, right? Do the same thing with the y terms. This time I'm going to factor out 4. Okay, so notice what happened now. Inside the parentheses, the x squared term and the y squared term have coefficient 1, positive 1. So now we can apply the completing of the square method. So let me write that down. Must be 1. Thus, we had to factor. We had to factor the x terms and the y terms. I worry that somebody might just download the lecture notes but not have the chance to watch the video. So I mentioned this in the video, but this is for anyone who just reads the lecture notes but didn't get a chance to watch the video. Okay, so now we can apply the completing of the square method. So we have 3 times. In order to complete the square, I'll have to say x minus 2x, once again, plus 1. So I added this 1 in order to be able to complete the square here. Give me that square. And then, so I have to subtract that as well. So minus 1, like that. So now I can complete the square here for what I've shown in the parentheses. Plus 4 times y squared minus 6y. In order to complete the square there, I have to have a plus 9 here. And I have to subtract 9 on the outside to balance this. So if you're wondering about how this is happening, so now we can write these 3 terms as a perfect square, which is what we want. But how to get from here to here? So basically, we first make sure that the coefficient of the square term is 1, positive 1. Then the b term, or the b, whatever it is, divided by 2. So in this case, it would be minus 3, right? So minus 3, then y minus 3 squared would be that. But I kind of, because we've covered that in Math 126, I didn't go through it in detail here. But please brush up on that topic. If you're confused about how we went from here to here, please brush up on that from Math 126, or just come by my office hours and I'll explain that. I'll go over it with you. And so then on the other side, then it would be equal to minus 39, right? So let's simplify this. We have 3 times x minus 1 squared minus 1 plus 4 times y minus 3 squared minus 9. I might, actually what I will do, at the end of this lecture, I will review this topic of completing of the square at the end of this video. So please hang on, watch the entire video. Once I finish talking about 11.4, I will do a quick review on this at the end of this video. I think that should be good enough too. And so equals minus 39. Okay, so now we have the perfect. So now let's distribute these. Well, in this case, let's see. What do I want to do? So. Okay, so let's do that. So we have 3, I'm going to distribute. So 3 times x minus 1 squared minus 3, distributing, plus 4 times y minus 3 squared minus 36 equals minus 39. So let's move the constants to the other side. So we have 3 times x minus 1 squared plus 4 times y minus 3 squared. On the other side, we have minus 39 plus 3 plus 36, right? We're moving the constants to the other side. What do we have on that side? We have 0. So we have 3 times that plus 4 times y minus 3 squared equals 0. Let's divide both sides by 12, right? Dividing both sides by 12. And we end up with this equation, x minus 1 squared divided by 4 plus y minus 3 squared divided by 3 equals 0. So look at the other side. The other side is, if you look at the left side, just the left side, it looks like an ellipse, right? But it's not, because the other side is equal to 0. And let me bring back, for the degenerate case, we said that if completing of the squares in the general equation leads to a negative number or 0, then we say that the general equation leads to a degenerate conic. Okay, so if we had left with a negative number, we would still have a degenerate conic, but we didn't. We didn't end up with negative something on the right side, we ended up with 0. So this is still a degenerate conic. Degenerate conic. Okay, that's what we call it. In other words, it's not any of those conic sections we've been talking about. Okay. I should maybe add a degenerate conic is a point. So maybe on this slide, say that a degenerate conic, I'll just add to it, a degenerate conic is a point. It's just a point. Okay, it's that. So we can say, we can add that to this statement here. So we have a degenerate conic here, i.e. a point. Okay, it's a point. Okay, so let us do another example of the same kind. For that equation, we want to complete this square again. Okay, so like before, we want to move all the terms that have variables in them to the left and leave the constants on the right side. So let's do that next. So x squared minus y squared minus 10 times x minus y, let me move this down a little bit, like that, equals 1. See, all I did was move this term 10 times x minus y to the left and left the 1 on the other side. So now let me distribute the negative 10 into that, because I need to separate the x and y terms in order to complete this square. So I need to distribute this. Now I'm going to put x terms and y terms together. So x squared minus 10x, and then minus y squared plus 10y equals 1. Now I'm going to factor out, to complete the square, the coefficients has to be, the squared terms have to be equal to positive 1. So this is okay, but that's not. So I'm going to factor out the negative from the y terms. Like that. Now we can complete this square. For this one, we have x squared minus 10x plus 25 minus 25. Again, at the end of this video, I will do a review of this method of completing of this square. And then minus y, that's the same thing, minus 10y plus 25 minus 25 equal to 1. If I add 25, I have to take away 25. Okay, that's the case always when we complete this square. Okay, so let's simplify this. So this is equal to x minus 5 squared. And I'm going to move the minus 25 to the other side. And so here, then I will have minus Let's complete this square here. Oops, this should be y squared. Sorry, y squared. So y minus 5 squared, but this minus times minus 25 is positive 25. So 1. When I move this minus 25 to the other side, it becomes positive 25. But this minus times minus, when we distribute this to both of these, it's going to make this positive 25. When I move it to the other side, it becomes negative again. So what we have x minus 5 squared minus y minus 5 squared equals 1, right? These two add up to 0. 0 plus 1 is just 1. Okay, so the denominators here are missing, which means this is they are 1, right? So what is the equation here? Which conic section this represents? Do you remember? So this is a hyperbola. And with the center at 5, 5, right? And A is equal to 1 and B is equal to 1, right? So that's that. Okay, so that's a hyperbola. This wraps up what we had to cover in section 11.4, but as I promised you, I will spend some time now to talk about completing of the square method. So, and I'm going to use, so this is a review. So this is an extension. So this would be page 13. And so review of the method of completing the square from pre-calculus 1 or MTH 126. Okay, so we're going to do that. And I will use this example to talk about that. I think this was a neat example, so let me, because we had to factor, that's what I'm saying. So we're going to be using this equation. Okay. So, first of all, in order to apply the coefficients of the squared terms should be positive 1. Positive 1. Okay, so here we need to factor to make that happen. So that's the first step we'll have to do here. Okay, so which we did before, but I'll go into more details here than I didn't before. So we're going to have 3x squared minus 2x, putting these together, right? And then plus 4 times y squared minus 6y and equals minus 39. So I think so far you followed from the example I did. But then how do we then complete this square here? Well, once you factor out this, once you have the coefficients of the square terms equal to positive 1, then you know with quadratic equations we had ax squared plus bx plus c equals 0, right? So recall, so this, take this coefficient of the x term and the coefficient of the y term. My students in Math 126 used to call this b. That's how they prefer to remember it, because a would be the coefficient of the quadratic term, and b would be the coefficient of the x term here and the coefficient of the y term here. So if you prefer to refer to this as b, that would be correct. So whatever this b value is, whatever it is, you always divide it by 2, always. So b divided by 2, in this case, b divided by 2. So that would be equal to minus 2 divided by 2, which is negative 1. Here it would be minus 6 over 2, which is minus 3, right? As soon as you do this, as soon as you divide b by 2 and you get this number, then you can complete this square. You say, in this case, we say x minus 1 squared. Here, what do we say? We say 4, that's 4 on the outside, 3 on the outside. 4 times y minus 3 squared equals minus 39, right? Notice I put a significant amount of blank space here. Why? Because if you expand this now, that's how we get what this number should be, that we're going to say x plus, or that if this was plus 5, I would say x plus 5 squared. If this was minus 1/2, I would say x minus 1/2 squared. If this was 19 over 2, I would say x plus 19 over 2 squared. So that step is very important. It tells us what that number should be, that we should either subtract or add in order to complete this square. But this process generates a third term that is not part of the original 2 terms. Let's expand it. So if I expand this one, right, this is, you can FOIL it or you can use the shortcut formulas. But if you expand this, you're going to get x squared minus 2x plus 1. Compare this with that. Are they the same? No. You by completing the square, you introduced a 1, which wasn't there before. So you need to take it away. So because you know that this process generates an extra 1, you say minus 1 here. Now you're okay. Now when you expand it, you get this 1, and this negative 1 can add up to 0, so it makes no difference then that you completed this square. You're not going to end up with a third term which wasn't there before. This minus 1 will cancel that, and you get this 2 terms. You got to do that same thing here. So if you expand this, right, what are you going to get? You're going to get y squared minus 6y plus 9, right? Compare this with that. Are they the same? No. You have an additional 9 that wasn't there before you completed this square. So in order to get rid of this 9, this extra 9, you say minus 9. Okay? Now, then we can distribute. We can distribute this 3 into this, and we have completed our square. So we end up with 3 times x minus 1 squared minus 3 plus, distribute that, plus 4 times y minus 3 squared. 4 times minus 9 is minus 36 equals minus 39. And now we can move the constants to the other side where we have negative 39 plus 3 plus 36. So we have 3 times x minus 1 squared plus 4 times y minus 3 squared equals 0. And then we divided both sides by 12, right? So we ended up with x minus 1 squared divided by 4 plus y minus 3 squared over 3 equals 0. So this is a review of method of completing the square right here. Right here is a complete review, and also that we factored out the 3 and the 4 here. Okay, so I'm going to show it like that. So you have the original expression here showing, and that we factored out 3 from the x terms, from these two terms, and factored out the 4 from the y terms. I hope this helped you remember what, if you didn't already know what the method of completing of the square is, then this should, going from here to here, should show you how we do that. Just remember, you cannot apply this method if the coefficients of the x squared terms is other than positive 1. So you know you're going to have to factor out that. Once you factor out and you get the squared terms that have coefficient equal to positive 1, then the b term, whatever it is, if it's a 17, you would divide it by 2. You divide the b term by 2, whatever that value that you end up with, you use that to complete the square. But that then you have, when you expand it, you should subtract the third term that you end up with. In each case, that third term will be different. Here we had plus 1, plus 9. It could be 100 over 13. Then you'd say minus 100 over 13. It could be 17 over 5. Then you'd say minus 17 over 5. Okay? Always. Okay, so thank you for staying with this video and set of instructions for the entire period, and I wish you a very nice day today, and see you again next time.